Every year, the Anopheles mosquito is responsible for more than 700,000 human deaths. Most of those deaths are caused by malaria, a disease that continues to overwhelm healthcare systems across the globe. Entomologist Bart Knowles has spent 22 years studying this insect, even going as far as letting lab populations feed on his own blood to better understand their behavior. Researchers like Knowles have found that the mosquito's success comes from a highly specialized biological toolkit designed to locate and infect human targets. This insect is a master of navigation and detection, possessing an efficiency that has allowed it to thrive for millions of years. To fight back, we have traditionally relied on wide-area fogging, spraying entire communities with insecticide to kill the adult population. This approach often triggers a genetic counter-response. When a small number of mosquitoes survive the spray, they pass their resistant genes to the next generation. Within a few breeding cycles, the local population becomes entirely immune, rendering the standard chemical sprays ineffective. Simply increasing the volume of poison is a failing strategy. The insects adapt faster than we can spray. Most malaria infections occur at night, inside homes that were never designed to keep mosquitoes out. Mosquitoes hunt by tracking carbon dioxide and human odors. At night, these scents drift out through the gaps between the walls and the roof. These open eaves act as a beacon, guiding the mosquitoes directly through the gaps and toward the people sleeping inside. By identifying this specific entry point, researchers realized they could use the mosquitoes' own hunting patterns to intercept them. The strategy involves concentrating the human scent into a single lethal bottleneck. The first step is sealing the eaves of the house. In their place, workers install plastic tubes equipped with a fine mesh screen. With the house sealed, human scent is forced through the tubes. Mosquitoes follow the smell and land directly on the mesh, which is coated in a concentrated insecticide. Because these tubes are placed high up, safely away from residents, researchers use much higher concentrations of insecticide than would be safe for indoor spraying. This heavy coating provides an immediate, lethal dose. By ensuring that every mosquito that touches the mesh dies instantly, there are no survivors left to pass on resistance. This targeted delivery allows for a complete kill, preventing the partial exposures that usually allow populations to evolve immunity. To test this in the real world, researchers modified 1,300 homes in Tanzania with these Eaves tubes. Over a 7-month period, field data showed that 100% of the mosquitoes that encountered the mesh were successfully eliminated. While the initial modification of a house is an investment, the ongoing cost of the program is remarkably low. Maintaining the system only requires replacing the small mesh inserts, bringing the annual cost down to between $1 and $2 per person. This affordability makes it possible to scale the technology across the world's most impoverished regions. Eaves tubes are designed to be part of a multi-layered defense, complementing the use of indoor residual spraying on interior walls. They provide an outer layer of protection that works alongside bed nets to keep mosquitoes away from families throughout the night. Expanding this grid of defenses could save millions of lives in Africa, Asia, and South America. We now have a practical, science-based method to outmaneuver one of humanity's most persistent threats. The success of the Eaves tube demonstrates that controlling malaria depends on interventions that account for the natural behavior of the insect.